Assalamu alaikum. Welcome to this session. In this session, our primary agenda is to talk about some practical aspects of applying learning algorithms. More specifically, we'll be talking about two important concepts, which are very much important from the practical perspective. They are called overfitting and underfitting of different learning algorithms. So before we dive a little deeper into the concepts which we are intending to complete today, let's set up some fundamentals. So we'll be talking about at the start two fundamental statistical measures. One is expected value. Expected value is a statistical name of mean or average. So theoretical mean of a random variable x over many trials is called expected value. And expected value is computed formally as uh, a sum over all i's. Xi is the value of that particular random variable, and probability of that random variable attaining value xi, they get multiplied, and we keep on multiplying them over all possible i's, and that gives us the average value of x or expected value of x. We use this capital E to notate expected value. So this capital E is kind of a notation which we'll be aggressively using in our upcoming discussion as well. So just to put this whole thing in a slightly informal way, if a fair six-sided die is rolled, the expected value is computed if we just plug in the values from the perspective of a fair six-sided die. So each side is equally probable. So Pxi for all xi's is going to be 1 over 6. और xi जो हैं they range from 1 to 6 in the context of a six-sided die. So 1 times 1 over 6 plus 2 times 1 over 6 and so on. So this gives us 3.5. So we know that when we roll a die, the expected value should be an integer from the linguistic perspective, but this expected value which we are trying to estimate over here is essentially the expected value from the perspective of mean. Okay, if we repeat this experiment, जो हमारा mean होगा, that will be around 3.5. Okay, the second statistical measure which we are going to talk about is variance. Variance is the expected value of the squared deviation of a random variable from its mean or expected value. So I have color coded over here things to make some intuition. So okay, so what is deviation? Deviation is that how far or how much deviated is the random variable from its own expected value. So x minus expected value of x, the content which is the expression which is put over here inside the parenthesis is the deviation of a random variable from its mean. X minus expected value of x is the deviation. And then we take a square of this one. Why? Like what? One quick intuition is that why are we interested in squaring it? And the one quick intuition is that x minus uh, expected value of x could be positive, could be negative, and over multiple trials, a positive value and a negative value might be canceling each other. So in order to take care of the difference, we are squaring the deviation over here. And amongst once that deviation is squared, so we are talking about the mean value of the squared deviation of x from its own mean value. So we are taking mean of the, again, the bigger term, which is square deviation of a random variable from its mean. So take a small pause over here, try to absorb this thing, try to relate the linguistic perspective with the mathematical perspective, and then we'll move forward. So if you were able to make some linguistic link between the mathematical expression and the linguistic expression, as far as definition of variance is concerned. So what we do now is that let's try to open it up. So we simply apply the square operation over here, and the inner expression, which was given in the parentheses over there, that becomes x squared minus 2 times x times expected value of x plus expected value of x ka square. So the next thing which we do is that we apply expected value across the entire expression separately because linearity holds for expected values. So this terms, so all these terms are separated from the perspective of expectation. Uh, so the first term just becomes expected value of x square. The second term, if you focus on the second term, that is expected value of 2 times x times expected value of x. So 2 is the constant over here. So that comes out over here, and then we are left with expected value of x times expected value of x. So the expected value of x, if we apply another expectation over here, so once we have taken mean of x, that is one singular value. And if we are taking mean of this, that singular value, that will remain same. So having expected value of x will give us same thing, expected value of x. And the first one is expected value of x. And then the same thing happens over here in the last expectation. That uh, expected value of x square is going to be one value. So expected value, square of expected value. So this is expected value of x. इसका square जो है that's one value and उसकी expected value will remain the same because किसी भी एक value का mean remains the same. So if you have been able to follow up with this algebraic expansion of the definition of variance of x, so now what we do next is that this central value term, this becomes 2 times expected value of x ka square, and we simplify it, and the final term, the final expression for variance is expected value of x square minus expected value of x ka square. So keep in mind that from the interpretation perspective or from all practical perspectives, both of these terms are different, right? एक जो लेफ्ट वाली टर्म है वो क्या है कि वी आर फर्स्ट टेकिंग वी आर फोकसिंग ऑन एक्स एज अ रैंडम वेरिएबल और एक्स का स्क्वायर है, दैट्स अनदर रैंडम वेरिएबल, उसकी एक्सपेक्टेड वैल्यू की हम बात कर रहे हैं, उसकी एवरेज वैल्यू की बात कर रहे हैं, ये मीन वैल्यू की बात कर रहे हैं। और द सेकंड टर्म जो है उसकी उसमें हम क्या करें, वी आर फर्स्ट कंप्यूटिंग द एक्सपेक्टेड वैल्यू ऑफ एक्स नॉट ऑफ एक्स स्क्वायर, और वो जो एक्सपेक्टेड वैल्यू ऑफ एक्स है दैट इज अ सिंगल वैल्यू, उस वैल्यू का हम स्क्वायर कर रहे हैं। सो दिस गिव्स अस द एक्सप्रेशन फॉर वेरिएंस ऑफ अ रैंडम वेरिएबल एक्स। सो इतना ही था जो हमने statistically these two definitions are going to be used in our coming discussion, so we wanted to get introduced to these two things. One was expected value or mean, or the second one was variance. Okay. Now from the machine learning perspective, inductive learning hypothesis is an important concept. And this hypothesis or this assumption is that any hypothesis found to approximate the target function well over a sufficiently large training data will perform well on the unseen data too. So this is the kind of stuff which you might have experienced in the programming assignments of the previous two topics as well. Okay, we have some training data. We train our target function on that training data, and once it has been trained, once the target function has been fine-tuned for the training data, then our assumption is that the same function will be good enough to do well on the unseen data, which is primarily the test data. So we use two terms. We're using two terms over here. One is training data. Training data is set of examples. And by examples, we mean that we are talking about pairs of inputs and their corresponding outputs uh, in the supervised learning setup. That set of example is used to learn the parameters of a machine learning model. So And the second type of data, which we are talking about in our inductive learning hypothesis definition, is the unseen data, which is test data. That's a separate set of examples used to evaluate how well a trained machine learning model generalizes to unseen data. So goal of a supervised learning task is that it has to come up with a function such that that function predicts outputs of x as close to y as possible. जितना y is the actual output, h theta x is the predicted one. So जितना prediction is going to be the actual one. So we are going to that's the like broader idea that's what we mean by learning, and particularly that's what we mean by supervised learning. Because supervised में major चीज ये है कि y is given to us. So what we do is that we learn parameters by minimizing the cost. We define a cost function. In the context of linear regression and logistic regression, we have already talked about two types of loss functions. So this term is a loss function. You can define this loss function as per your choice. Could be mean squared error, or could be cross entropy in the context of logistic regression, or you might be coming up with your own customized loss function. So, but loss function की जो primarily दो parameters हैं, they are के जो आपकी predictions हैं और जो आपका एक्चुअल डेटा है, जो एक्चुअल लेवल है इन द ट्रेनिंग डेटा, उसके ऊपर you compute the loss, that how much you are deviating from the target. And we m is the number of training examples, so we do this entire computation over the entire training data set, and we compute our loss function or cost function. So our objective is to minimize this cost function. So now the question is that will the model perform well on unseen data? If you expose your trained model, which used this loss function or cost function using a training data set, how good would it be to perform in a reliable way on unseen data or on test data? And if it succeeds, so we will start using the term of generalization that our model is doing well. Now, there are two critical concepts which we are going to discuss in the next uh, part of the lecture. One is underfitting, other one is overfitting. So underfitting is a phenomenon which refers to this notion of model being too simple. And when we say a model, the model which has been trained is too simple, that means that it is unable to capture the exact relationships between inputs and outputs of the training data. And as a result, it induces high training error. So which means that during the training part, the data which was being used to fine-tune the model could not really converge in a decent way. So in an abstract way, if the model is too simple, we call this phenomenon as underfitting. We'll be seeing its visualization in a while. The flip side is that if our model somehow, during its training phase, during its entire training exercise, it becomes too complex and it fits very well to the training data, which also means that if there is some noise in the training data, that also fits to noise. And as a result, it results into a very low training error, but might be ending up in very high test error because it tried to fit itself very closely to the training data, and as it attempted to get as close as possible to the training data, including noise, the phenomenon was somewhat that it started getting closer to memorization. So somehow it started memorizing the training data uh, while being a very complex model during that entire memorization process. And as a result, we ended up into low training error. But as the model was exposed to some unseen data, it, it might be resulting into high test error. So these are two extreme situations. And our task as a machine learning engineer would be to find the right model complexity. We have to avoid oversimplistic models. And at the same time, we have to avoid over complex models because both of them have their own pros and cons. And let's try to have a look at that. So if you focus on the figure which is on the left side of this screen, it's a classification situation. And our task is to classify these crosses with against circles. And during the when we so this these crosses and these circles are essentially representing the training data. So as we expose our learner to learn the underlying pattern, so it simply fits a straight line. So fitting a straight line on this data, and you can see over here that the boundary between these two classes is not really a straight line. So this is the kind of phenomena which we call that this is a very simple model and we are ending up into underfitting. And now if we jump to the figure which is on the rightmost side, that's an opposite thing, that there's a complex learning happening over here. The the separation between the items on both sides, items of two classes, is being done at a very fine-tuned level. It's somewhat very close to memorization. So the model is getting over complex, and by over complex, you can see the shape of the red line, which is essentially separating the data items between data items of two classes. So it's so cleanly fitting to the data which has been provided for training purposes that it ends up into zero training error practically. But the underlying actual phenomena might not be that complex. This red learned line might not be good representative of classifying items of these two classes. So over here, the model has gotten over complex, and the training error is zero practically in this visualization or in this example. So if we, for example, if I just bring in some small uh, new item over here. So let's say our next circle is over here. So it will get immediately into the other class. So we'll be ending up into, or if I have something over here, so we'll be like throwing them out of the class, their respective class, and we'll be landing into incorrect predictions because the model is over complex and it has somehow memorized the training data. So it's not good enough for the test data. So this is another extreme which we need to avoid. This is what we call overfitting. So now if you look at the figure which is at the center, that is if you look at the model, which is the red one, so this concept is, as far as the complexity of the curve is concerned, as far as the complexity of the learned curve is concerned, this is somewhere between both of those two extremes on the left and right side. So this is not a like oversimplistic kind of situation. It's neither it's not even a like very complex kind of situation. So over here, it did not mold itself to adopt to some data points which are not making a very good sense in that entire training process. And what do I mean by that thing? If you look at these two processes, for example, they are somewhat, we call these kind of data points as noise, right? So they are actually placed within the circles valley class, but they actually don't belong to that class. So most probably this is noise. So those are illegal or inconsistent data points. So somehow the ideal model should be able to ignore them or should be able to filter them out during the learning process. But rest, so if we, including those 2 points, if you compute the training error, so that's not zero because these two are getting misclassified. But for the kind of new data points, जिस तरह के pink circles मैंने पहले draw करने की कोशिश की थी. So if I draw some more pink circles on over here on this side or over here, so the chances are that the learned model, this trained model will be able to classify these bubbles in a better way as compared to underfit or overfit models. So as a machine learning engineer, our like important practical consideration should be that we have to go for an appropriate balance between these two extremes. Now, this is ICP time, so we have a bunch of ICPs. I would strongly suggest that after every question, you should pause the video, ponder upon the question. That will help you to get engaged with the content and clarify your concepts. Though the answers will pop up on the slides in a while, but if you try to figure out on your own, that would be great. So the first ICP is that what is the total training loss of green curve? You need to analyze this figure, which is given on the slide. There are red dots. So each dot is a training data point, and there are two curves which are uh, shown over here. X is the input side, Y is the output. What is the total training loss of green curve? So if you pause the video, and you might have figured out by just inspecting this figure that the loss is zero, because during this entire training process, the green curve is perfectly fitting the data parts. It's not missing any data part. So the value which green curve would predict for each of those data parts is exactly same which it should have been as given by the red part itself. What is the total training loss of blue curve? So if you pause the video, you might have figured out that this is also zero. And over here in both of these ICPs, we didn't really bother much about defining a particular loss function in order to compute the answers, because from the visual inspection, we can see that both of the curves are actually perfectly managing the training data. So during the training process, both of them are leading to zero training loss or zero error. Now, the important question is that are they equally good? I would strongly suggest to pause the video over here and think. So if you pause the video, you might have come up with this thing that they're not equally good, as we could see from their shapes. So they are not equally good. So why are they not equally good? Because blue curve is unnecessarily fluctuating. And why is this unnecessary fluctuation problematic for us? Again, pause the video, try to figure it out on your own, that why is this unnecessary fluctuation a problematic thing for a learner, for a learned model? Because it does not generalize well over the given training data. And what does that mean? That means that if I have, like, for example, a new data point, which is somewhere here, right? Or another data point, which is somewhere here. So this green curve should be able to predict the output with low error. But if I think of the blue curve, so if my data point is over here, so the blue curve का जो prediction होगी, that is far away from that actual thing. Same is the kind of thing which is happening for the second data point, that my prediction for the green curve is going to be over here. But for my prediction for the blue, using the blue curve for the same data point, is going to be at a like far away place. So that's what we mean by generalization, that the model is not going to, the blue color model is not going to generalize well over, it's not generalizing over the given training data, because जो blue वाली curve है, that does not really show the spread of data, though somehow it has memorized, and most probably it used some complex underlying relationships, and it overused them, and that resulted into this kind of shape of the learner. So both of these curves are essentially the models. One of them is like generalizing reasonably well, the green one, and the blue one is not really generalizing because of those extreme fluctuations. Okay, now using our fundamental statistical definitions, we are going to define two more terms over here from the model's perspective. One is bias, other one is variance of the model. So bias is that on average, how far are your model's predictions from the ground truth? When we say ground truth, by ground truth, we mean the actual output, actual wala y. And when we say predictions, that's what we mean by predictions, we mean y hat. So when we compute the bias, that's that how far are your model predictions from the ground truth. So the expected value of the prediction is computed using our fundamental formulation of expected value LGs. So model की जो predictions हैं, they are being modeled as expected value of the prediction minus the ground truth, which is by. So this is what gives us the idea of is our model a good model in terms of bias. So if the bias is low, so from bias perspective, at least the model seems good because model's predictions are close to the ground truth. The second part is variance. And by variance, we mean that how much do the model's predictions vary? Now, if you focus on this linguistic part, so it's not talking about ground truth. It is just saying that within that entire pool of predictions, how much is the how much is the variation? So more specifically, variance is computed as an expected value of squared deviation of the predictions from their mean. So if you are able to recall the fundamental definition of variance, जिसको मैंने थोड़ी देर पहले derive किया था, so this is exactly same definition. Over here, our random variable is now the prediction. So our prediction is y hat. So we are using कि हमारा जो random variable y hat है, how far is it from its expected value, and that's the deviation of that random variable from its mean. We are squaring it, और उस square की जो expected value है, that's what we call variance. और फ्रॉम द इंटरप्रिटेशन परस्पेक्टिव व्हाट डू मीन बाय वेरिएंस इज कि हमारी जो मॉडल की प्रिडिक्शंस है ना उनका स्प्रेड कितना है. सो यू माइट हैव फिगर्ड आउट ऑन दिस प्रीवियस स्लाइड कि हमें जब आप फर्स्ट वाली जब डेफिनेशन को देखते हैं बायस को तो हमें लगता है कि लो बायस इज गोइंग टू बी समथिंग ऑफ आवर इंटरेस्ट. And when we say variance, again, low variance is going to be of our interest so that we can say the model is reliable. But if there is high bias and high variance, so they are essentially main contributors to the prediction error. So हाई बायस अब कहाँ से आएगी? हाई बायस का क्या मतलब है? हाई बायस का मतलब ये है कि हमारी जो एक्सपेक्टेड वैल्यू ऑफ द प्रिडिक्शन है that is far away from the actual output or the ground truth. So model is too simple and has been unable to capture the underlying data जिसके ऊपर वो ट्रेन हुआ है. तो that induces high bias. Model variance की रीजन ये होती है कि मॉडल इज टू सेंसिटिव टू ट्रेनिंग डेटा एंड फिट्स नॉइज. और जब प्रिडिक्शंस आती हैं तो दे डोंट रियली रिप्रेजेंट the the actual situation, the actual relationship between the inputs and outputs. They are more like memorized kind of thing on the training data. और जो unseen data आता है तो उसके ऊपर उसका spread is like all over the place. So our task would be that we need to, so as we go along, not in this session, but like in the coming sessions, we'll be talking about the trade-off between bias and variance. We'll be having a detailed discussion on this part. But like, let's have a quick view that in order to diagnose that what are the consequences of high bias and high variance. So if there's a case of high bias, so that takes us to high training error. Right? Quickly recall कि bias होती क्या है? Bias is a deviation of your prediction, expected value of the prediction from the ground truth. तो अगर आपकी जो predictions हैं और जो ground truth है, if they are far away from each other, तो high bias है. तो that induces high training error. Even on the training data आपका error high होता है और जो आपका validation data होता है which is not directly used during the training process, उसके ऊपर भी आपका जो error है वो high होता है. Okay. If variance is high, तो if variance is high, तो that means कि आपका जो expected value of predictions हैं, they are like spread over all over the place. उनका spread is like pretty wide, which means that is going to induce a high error on validation data, which is not been used for training, but it gives us it can give us low training error. And the ideal balance would be that we need to come up with a model where we need to control bias, we need to control variance, so that we can reduce both the training error as well as the validation error. Okay, now if we closely follow what is here on this screen, this is essentially a kind of explanation of the descriptive part जो हमने अभी देखा है. So let's have a look on these four parts of the figure one by one. So think of each of these boards as a darts board. Dart board होता है जिसके ऊपर you throw the darts, और आपका target ये होता है कि you actually want to hit the center, right? Or अगर if you repeat that experiment few number of times, how good have you been in hitting the target? So अब हम ये कह रहे हैं कि this is a situation where bias is low. Bias क्या है? आपका आइडियल टारगेट क्या था कि यू वांटेड टू हिट द इनर सर्कल, और आपकी प्रिडिक्शंस क्या हैं? वो हैं जो आपने एक्चुअली थ्रो किए डार्ट्स, वो लगे कहाँ पे हैं. तो ये जो अंदर वाले स्क्वायर्स हैं, रेड स्क्वायर्स हैं, दे आर एसेंशियली रिप्रेजेंटिंग द प्लेस जहाँ पे आपके डिफरेंट डार्ट थ्रोज लगे हैं. सो इफ ईच थ्रो इज hitting the target, तो आपकी bias is going to be low because you are not deviating from the target. Or across multiple trials, if the spread within those dart throws is also low, तो this is a low variance situation. So actually this is an ideal kind of situation कि हमारा जो ग्राउंड ट्रूथ था, जो हमारी डिजायर्ड जगह थी, हम उसके भी क्लोज हैं, और विद इन द प्रिडिक्शंस भी आपकी वेरियंस is controlled, is low. Now, if we move to the figure which is on the right side over here, what is happening over here? Bias is still low. Why is bias low? Because if we average out things over here, so this is relatively low. We are somewhere around the target. So our target was again innermost circle. So we are either inside the circle, on the border, or just around it. So bias is relatively low, but as you can see, the difference between the red boxes is more than the previous figure, which means we are inducing higher variance as compared to the previous situation. And if we look at the left figure on the bottom over here, so this is a high bias वाली figure. High bias का मतलब है कि your deviation from the target is high. So your target was here, but you ended up over here. Your dart throws are hitting here. So which means you are ending up into high bias. But within all those throws, उनके जो आपस का spread है, that is low. So that's why it's a low variance वाला column. And if you look at the last one, which is the actually relatively bad situation where your bias is high because you were supposed to hit this place, but आपकी जो dart throws हैं, they're not really hitting the target. Right? Two of them are hitting, but on average they are like pretty much, if you compute the cumulative bias, so they are like pretty much off the target. And within those dart throws, there is a reasonable spread. That means that you have somehow induced high variance as well. So this last figure is a figure representing high bias as well as high variance, which is a kind of worst situation where a model can end up. So as a machine learning engineer, it would be our target to design something, to model something which is close to this kind of situation where bias is low and variance is also low. By once more, कि bias low का क्या मतलब होता है कि हमारी जो predictions हैं, they are close to the target, they are close to the desired ones, and within those predictions the spread or the variation is pretty much controlled. इनका और मैथमेटिकली अगर आप देखें ना, तो इनका जो ईच प्रिडिक्शन है, इनका जो मीन है वो यहाँ पे है. इनका जो डेविएशन है फ्रॉम देयर ओन मीन इज रिलेटिवली लो एज कम्पेयर टू जो राइट साइड वाले दोनों फिगर्स हैं. यहाँ पे आपका मीन है, और आपका जो डेविएशन अराउंड द मीन है, दैट इज वाइड, सो दैट इंड्यूसेस हाई वेरिएंस. So learning curves are actually helpful to analyze these kind of problems. Uh, So we can see that how the models are behaving with the change in the training data, or more specifically with the change in size of the training data. If we somehow provide more data, more training data to a model, will that help or not? So training error is essentially the error which is the error computed on the training data set. क्रॉस वेलिडेशन हमने वैसे, दिस इज आवर नेक्स्ट टॉपिक जो हम इस अगले वाले सेशन में पढ़ रहे होंगे इन डिटेल। क्रॉस वेलिडेशन क्या होती है, बट उस वक्त तक आप ये इसको समझ लें कि दिस वैलिडेशन एरर, विच मीन्स कि ऑन अनसीन डेटा के ऊपर जिसको हमने एज सच डायरेक्टली ट्रेनिंग के लिए यूज नहीं किया, उसके ऊपर हाउ गुड और बैड इज द मॉडल्स परफॉर्मेंस। So a data set size as data set size increases, training error usually increases slightly. Why? Because जब ट्रेनिंग डेटा आपका छोटा होता है ना, ट्रेनिंग डेटा का साइज जब थोड़ा होता है, तो देर इज रीजनेबल प्रोबेबिलिटी कि आपका मॉडल विल बी leading towards something which we call overfitting, or in other words, model might start memorization। और जब आप उसको ज़्यादा डेटा देते हैं तो फिर उसके लिए मुश्किल हो जाता है सारे डेटा को मेमोराइज करना, और देन फिर वो जब थोड़ा सा अपने आप को जनरलाइज करने की कोशिश करता है तो आपका ट्रेनिंग एरर थोड़ा सा बढ़ता है, बिकॉज वो मेमोराइजेशन से थोड़ा आगे जा रहा होता है। वैलिडेशन एरर यूजुअली डिक्रीजेस uh, when you provide more training data in terms of size। तो बिकॉज मॉडल आपका जो ट्रेनिंग के दौरान जनरलाइज कर रहा होता है, तो चांसेस आर कि वैलिडेशन या अनसीन डेटा के ऊपर जो उसकी परफॉर्मेंस है, दैट विल गेट बेटर। And in terms of visualization, let's try to analyze this visualization over here. On the x-axis, we have training data size. On the y-axis, we are observing the error. जो जो ट्रेनिंग डेटा सेट का साइज बढ़ रहा है फ्रॉम लेफ्ट टू राइट, तो देयर आर टू कर्व्स व्हिच वी नीड टू लुक एट। वन इज द ट्रेनिंग वाली कर्व, द अदर वन इज द वैलिडेशन वाली कर्व। ट्रेनिंग कर्व का मतलब ये है कि हमारा जब ट्रेनिंग डेटा सेट साइज छोटा था, तो उस वक्त ना बड़ी परफेक्ट किस्म की ट्रेनिंग एरर था, बहुत लो था। बट वैलिडेशन एरर वाज हाई, बिकॉज यहाँ पे इस वाले रीजन में ऐसे चांसेस लग रहे हैं कि मॉडल वाज प्रेटी मच memorizing things for the training data set, or it was like failing on the validation set। But as we kept on increasing the training data size, तो उसके बाद क्या हुआ कि हमारी जो ट्रेनिंग का एरर था दैट स्टार्टेड इंक्रीजिंग, बिकॉज अब मेमोराइजेशन से चीज़ें बियॉन्ड जा रही हैं। और जो वैलिडेशन का एरर था दैट स्टार्टेड सेटलिंग डाउन, वो थोड़ा कम होता गया। और अगर आप आगे जाके देखें तो दे गेट दीज टू एक्चुअली गेट वेरी क्लोज टू ईच अदर, दोनों कर्व्स जो हैं। और उसके बाद pretty मच फ्लैट हो जाती है। फ्लैट होने का मतलब है कि इफ यू ऐड मोर डेटा बियॉन्ड दिस डॉटेड लाइन, तो इट डज नॉट रियली हेल्प टू इम्प्रूव द परफॉर्मेंस ऑफ द मॉडल। और वहां पे आप रोक सकते हैं कि बस दिस दिस मच अमाउंट ऑफ ट्रेनिंग डेटा साइज इज नाउ सफिशिएंट अनफ। इसके बाद जितने भी आप डेटा देंगे, तो दैट्स नॉट रियली गोइंग टू हेल्प मच टू ट्रेन दैट मॉडल और ऑप्टिमाइज दैट मॉडल। Okay, so when training error is high and validation error is also high, so जब दोनों एरर्स हाई हैं तो दैट मीन्स कि देर इज स्मॉल गैप बिटवीन देम, एंड that is the kind of situation where our learned model is very simple, and that takes us to the phenomena of underfitting. So possible solutions could be that we can add more features, use more complex model, because we are already landing into an underfit model which is very simple. So we need to make it slightly more complex by bringing in more features, or और वो फीचर्स कहाँ से आएंगे, we might have ignored some features while training that model at the start, या we might need to think of some complex relationships between the existing features कि उनको use करके how we can add complexity into the model। Or there is a phenomena of regularization which we are about to have a look at today। So we might have done too much regularization, so we need to control that if the model is leading to an underfit model। So if you visually have a look at that, on the x-axis we are seeing epoch. Epoch means how many iterations are being performed during that training exercise, and on the y-axis we are seeing the error. So when we say कि दोनों errors जो हैं ट्रेनिंग का भी और वैलिडेशन का both of them are high, तो you can see over here कि even after a reasonable number of epoch, after a reasonable number of iterations over here, दोनों जो कर्व्स हैं ना वो नीचे नहीं आ रही, एरर इज रीजनेबली हाई, ब्लू वाला एरर भी और रेड वाला भी है. रेड वाला इज द ट्रेनिंग लॉस, अदर वन इज द टेस्ट लॉस, or they are, because both of them are high, so there is a small gap between them. So this is a kind of pretty weak model which is not going to be of much help. ये जो जिस डेटा के ऊपर आप ट्रेन कर रहे थे उसके ऊपर भी इसने कुछ ज़्यादा अच्छा लर्न नहीं किया. इट्स नॉट fitting the concept, it's not fitting the, it has been unable to capture the relationship between input and output on the training data, and at the same time चूंकि वो ट्रेनिंग अच्छा नहीं हुआ तो it has been unable to perform reasonably well on the unseen data, जिसको हम validation error कह रहे हैं. Another situation could be that your training error is very low but validation error is high, and because one error is very low, other one is high, so that leads to a large gap between those two errors, and that's the other phenomena जिसको हमने overfitting कहा था. तो हम underfitting और overfitting की को from a different viewpoint देख रहे हैं. We are talking about, actually we are talking about the same definitions जो हमने थोड़ी देर पहले की थी. So model memorizes the training data, that's what we mean by overfitting. To overcome this issue of overfitting, we can increase training data. We can reduce model complexity if it has already become too over complex, and we can increase our regularization factor. Regularization को भी हमने देखना है. So on the x-axis, we are increasing the number of iterations of the training process, and you can see that after a few iterations, ये जो आपका training error that settles pretty much. So वो almost flatten हो गया है. और जो वेरिएशन एरर है ना उसका भी डिक्लाइन जो है वो आगे जाते जाते ना फ्लैटन की तरफ जा रहा है. सो जो जो गैप है दोनों एरर्स के दरमियान, दैट इज प्रेटी ह्यूज. व्हाई दिस रेड वाली लाइन इज लाइक yielding लो एरर, बिकॉज वी आर डूइंग समवट लाइक मेमोराइजेशन विच इज कॉल्ड ओवरफिटिंग. और ओवरफिटिंग का मतलब है कि आपने ट्रेनिंग डेटा के ऊपर सब कुछ ऐसा याद कर लिया है, बट जी अनसीन क्वेश्चंस आपके सामने आते हैं तो यू फेल टू आंसर देम, एंड दैट्स व्हाट इज द ब्लू curve which is shown on top of this visualization. Okay, so how to make a model more complex? So for example, if the model was previously linear, we can make a polynomial model out of it by inducing additional learning parameters. So if there was x, तो अब हमारे पास और features तो नहीं है, but we can think of different relationships between x, like theta naught plus theta 1x plus theta 2x square minus plus theta 3x cube and so on, right? So you can increase the degree of the polynomial in order to induce more complexity. But keep in mind that if you make it over complex, that might be leading us to memorization of the training data, जो कि overfit हो जाएगा. So we need to create a good balance between them. Okay, so high degree allows the model to capture nonlinear patterns, and obviously it also makes it more complex. So now the question which you need to think, and if you have been like watching this video, and you can assess yourself, okay, how good were you to absorb the content which we have talked about so far. So take a pause and figure out the answer of this question. The question was, are higher degree choices of models always a better choice? So if you keep on making more sophisticated models in terms of complexity, by sophistication I mean कि आप linear की बजाय polynomial model fit करने की कोशिश करें, तो are they always going to be a good choice? So I hope you would have come up with the answer. The answer is no, they may cause overfitting. This is what we just saw on our previous visualization as well. Okay. So let's study effect of the polynomial degree. So if your polynomial degree is low, if it's a like simple model, so it may be, we've seen that it may take us to the situation of high bias or underfitting. If it's a moderate degree, that's a good generalization. If it's a high degree, that's a high variance, that's overfitting. So again, our task as a machine learning engineer would be that we somehow need to create a balance within the complexity of the model. So as you induce more complexity, that means we are moving towards a higher degree of polynomial. So we need to manage a moderate degree. So understanding these concepts from theoretical perspective is not a like very difficult thing, but like from practice, uh, this actually needs a careful thought and different levels of experimentation to land onto a moderate model, which should be able to generalize well on unseen data as well. So now take a pause, answer these questions. Why does low degree polynomial cause underfitting? So if you pause the video, you might have figured out that due to lack of capturing the underlying relationships between inputs and outputs, the low degree polynomial will be ending up into a higher bias. And why does high degree polynomial cause overfitting? If you pause the video, you might have figured out that due to attempting for a perfect fit, it actually starts in that attempt of perfect fit, it starts memorizing the training data, and that makes it a highly complex model. Now, over here comes in the idea of regularization. So, overfitting often occurs when parameters become large. और वो आपको जो blue वाली curve थी in the first ICP, you might have seen that kind of thing as well, because if parameters become large, they might cause fluctuations in your learned concept. So regularization is the phenomena which advocates that we should penalize large parameter values. And when we say penalize, that means that in our loss function, we introduce a regularization term. So R theta is the regularization term, and this regularization term is controlled, or its strength is controlled by lambda. So lambda is called uh, control parameter for the regularization term. So when we say we penalize large parameter values, that essentially means that we are adding this regularization term in our loss function, and we are modifying our loss function. So this is a regularized loss function, which we need to minimize. So now, what is r theta? This could be this is a function of theta, and you can come up with different regularization strategies of your choice. There are like different strategies available in the literature. Two famous regularization techniques are, one is called ridge regularization, also called L2 regularization. This is that r theta is if it just does like sum of squares of theta, and as a result, this r theta gets included in the modified loss function. So lambda times sum of squares of theta will give you the regularization term, and will get added up in your conventional loss function. So we'll call it regularized cost. So the properties of ridge regularizations are that it shrinks parameter values, keeps all features into the game but reduces their influence, and works well when features are highly correlated. The second alternate, which we are going to have a quick look at, is called lasso regularization, or also called L1 regularization. So over here, instead of taking the square of different parameters, we take their absolute values and we sum them up. So again, this r theta gets plugged in over here in the modified loss function, and its strength is controlled by lambda. So it shrinks some parameter values exactly to zero. What does that mean? That when we are talking about the absolute value, that means that some of the parameter values can, uh, when they become zero, that means that we are essentially performing feature selection. We are extracting, we are making some features uh, contributing to the decision, and some features will become neglected because their parameter values will be exactly zero. So theta times that particular parameter will go to zero, and essentially that will be completely neglected. So only a few features that are important remain effective in this kind of regularization scheme. And you can also design your own regularization scheme for a particular केस स्टडी और फॉर अ पर्टिकुलर स्पेसिफिक प्रॉब्लम जो आप उस पर रिसर्च कर रहे हैं जो या कोई और काम कर रहे हैं. सो यहाँ पे जो लेमडा है हमारा रेगुलराइजेशन पैरामीटर दैट आल्सो हैज सम इम्पैक्ट. सो इट इज वेरी स्मॉल दिस लीड्स टू पॉसिबल ओवरफिटिंग. When it is very small, what does that mean? That means that it is somehow very minutely tuning the parameters using the training data set. So it may possibly land to overfitting. And if we are choosing a very large value of lambda, that might be leading to underfitting because it might be dominating the underlying relationship which is being captured between the input and outputs of the training data. So again, over here, the task as a machine learning engineer would be to come up with a moderate value of lambda. So you have to choose lambda carefully. Now, again, ICP time. Try to figure out the answer of this question on your own. Why does very small lambda lead to overfitting? The regularization term becomes negligible. So the model is free to choose large parameter values to perfectly fit the training data, including noise. So because if lambda is very small, lambda times the regularization term irrespective of which regularization scheme we are using, that will become negligible, and the existing conventional loss function will keep on dominating. So if it was already overfitting, it may still go for overfitting the data as well as the noise. Why does very large value of lambda lead to underfitting? Pause the video and try to answer the question. This is the last ICP for today. So if you pause the video, you might have fit it, and the answer is actually obvious in the table given above. Uh, the model becomes overly simple, uh, and the impact of theta actually goes to almost zero, and that value of lambda actually starts dominating the learned model, and it fails to capture the real relationship between the inputs and outputs of the training data. So if in the context of logistic regression, you can optimize the standard logistic regression with regularized version. So we know that in the context of logistic regression, our hypothesis is that we pass theta tx through sigmoid, which is being represented as function g, and our regularized cost would be that in our cross entropy formula, we'll be adding this pink term of L2 regularization. So that's how our J theta will be updated. And as we update our cross entropy function, that will be having an impact on its derivative. So the gradient will also get updated. So you might have noticed that we are with lambda, we are dividing a term over here. We're taking half of that entire term, and that actually helps us in computing this derivative. It makes things simple. So we are left with just lambda over m times theta j. And the last comment over here is that the bias parameter, which is theta naught, is not regularized when we apply the regularization uh, on our loss function, and that results into the changes in the update rule. So that's it for today. So our next topic is going to be, we'll be talking about setting up our data set for our learning algorithm, what kind of stuff we need to take care of while deciding a training data. We'll be like diving a little deeper into what is the difference between training data, validation data, and test data, how to split them, what are the kind of consequences, and what are different validation techniques And the next topic after that topic would be that how to evaluate a learned model in terms of regression as well as classification. So we'll be talking about different evaluation measures once we are done with the cross validation stuff. Thank you.